Today I'll be discussing about the unit 11, which is block 3 statistical thermodynamics, where we'll be discussing about the partition function, definition and evaluation of translation, rotation, vibration and electronic partition function for monoatomic and diatomic and polyatomic gas molecules. So this unit mainly deals with the partition function. And next unit I will be discussing about the calculation of thermodynamic function, equilibrium constant, terms of partition function. There are different terms, so that we are going to be discussing. And entropy of monoatomic gas. There are two different laws are there compared with the third law of thermodynamics and statistical entropies. So heat capacity behavior in the solid also we'll be discussing today. And coming to the unit 11, that is mainly the partition function. Here we'll be discussing about the partition functions and their derivations. First, you should be knowing what is partition function. It is the ratio of the total number of particles. It is the ratio of the total number of particles to the number of particles present in the ground state. The particles are present in the different energy level. Ratio of the total number of particles present to the number of particles present in the ground state. So that is known as partition function. The partition function comes from a way of counting the particles. The particles are distributed over the different energy levels. To count these particles, they'll be represented by n. So n is the total number of particles present in the different energy level. Yeah, the significance in this unit, you are going to discuss about the significance of partition function, calculating the molar partition function and translation partition function, rotation of partition function, vibration of partition function, electronic partition function, and total partition function or molecular atomic partition function. So you should be knowing what is partition function here. It is the ratio of total number of particles to the number of particles in the ground state. That is known as partition function. So it plays a very important role in statistical mechanics. There are key to calculate the thermodynamic function. The mathematical definition is given by Q is equal to summation of Gi into e to the power of minus sin Ei into Kt. So Gi is the degree of energy, Q is the number of thermal accessible energy, and Ei is the pattern of energy level, and T is the temperature. Molecules will be distributed themselves over available energy level according to the Boltzmann distribution law. So molecules will be distributed themselves over available energy level. And this is about the partition function. And partition function, here we are going to take the derivation here, considering a gas containing n molecules, where n molecules will not possess the same energy. It will be in the different energy level. It can be calculated is equal to Ni, because N0 will be E0, energy level will be E0, N1 is the E1. So overall we will be taking it as an Ni. Ni is equal to N into Gi e to the power of minus Ei by Kt divided by summation of Gi into e to the power of E minus I divided by Kt. That is the equation 95. So here N naught molecule having the energy level E naught. That is the explain N naught will be and N naught molecules will be having the energy level of E naught. N1 will be having E1 and N2 will be E2. So that is denoted by Ni. And in the next equation 97, there is from wave mechanics that even absolute zero of the temperature of a molecule. So here mainly addition function we are deriving with the molecules which is varying for different temperatures. So for absolute zero of the temperature, a molecule will have definite amount of energy called zero point energy. Uh, this wave mechanics that will be in the three-dimensional, the particles will be bombarding from x, y, and z axis. So the mechanics, wave mechanics that even at absolute zero of temperature, a molecule will have definite amount of energy that is known as zero point energy, where E naught is the zero point energy and Ni is equal to N naught. That is the equation 98, where E naught is the zero point energy. Here, partition function actually tells us how the molecules in a system are partitioned between various energy levels. The molecules, how it is partitioned between different energy levels. The partition functions will say. So, here from the mathematical for n is equal to it is the total number of molecules n naught plus n1 into n3 till ni. So with respect to E is the energy present in the different molecules. So that is derived here in the equation 98, where Q is equal to summation of Gi e to the power of minus Ei by kT, and it is known as the partition function. And Q is the molecular partition function. So this is the about partition function. So next we are going to molar partition function. So it is denoted by Z. It deals with the large scale system in which the amount of substance are in the grams per moles. So it mainly deals molar partition function. How you are going to get means it for the molecules which are in the large quantity, the amount of substance are in the grams per moles. So here we are going to consider a system which may be supposed to constitute a large number of small ones and which can be in the grams per moles. So the average energy here it can be calculated. E is equal to summation of xi into ei divided by summation of xi. So that is the partition function from the previous, where summation of e to the power of minus ei divided by kt. This for the partition function, where z is the molar partition function, q is the q which denotes the molecular partition function, n is the Avogadro number that we are calculated for grams per moles here. And next is the determination of partition function. So to determine the partition function, so here the total energy ei possessed by a molecule, the total energy ei possessed by a molecule is contributed for various types of energy such as transitional denoted by ETR and ER that is for rotational and EV is for energy in vibrational energy, and E is the electronic energy. So different energy has been liberated, while ETR is the translational energy, ER is the rotational energy, and EV is the vibrational energy, and E is the electronic energy. So for two or more atoms uh, are known as polyatomic. Polyatomic molecules are nothing but two or more atoms, except for nitric oxide or oxygen. So here the electronic contribution to the total energy can be ignored at ordinary temperature, but at high temperature it contributes to the quite considerably. So at low temp, it is meant for the not meant for the low temperature. Up to a certain high temperature, this partition function can be derived. So some of the molecules which are having low temperature while in the reaction cannot be get the partition function values from this. What we are going to get, why you are going to get the partition function? Because we are going to calculate the ratio of total number of particles in the number of particles present in the given energy in the ground state. So this is the equation where it can be written EI is equal to these are all the representatives where EI is equal to EI is the partition function is equal to energy of transitional energy plus rotational energy, and this is the vibrational energy, and this is the electronic energy. So further substituting, you will get the value of Q is equal to this mathematical. You go through this. If you go and understand, you practicals ಬಂದಾಗ ಕೇಳಿ ಅಷ್ಟೇ. This for the transition and rotation partition function, vibrational partition function, and this for electronic partition function. It can be written where it has been denoted by Q, P, QR, QV, and QE, and can be this the equation where Q is equal to and further taking the for the equation 103 taking the log on both the sides, it has been calculated, and he is the nothing but the total energy with CV is the heat capacity at constant volume. And next is the translation partition function. So here all kind of molecules for monatomic as well as polyatomic possess translational energy. So quantum mechanical expresses for the translation of energy per molecule. The translation partition function of a molecule is denoted by QTR, and N is the translation quantum number, this N, and M is the mass, and L is the length of the container. So if you take in a system is nothing but a container where we are going to calculate the mass temperature of that particle. N is the transmission quantum number and M is the mass. And for this equation 104, where QTR is nothing but the translation partition function is equal to summation of GT or e to the power of minus ER 1 divided by KT. On taking statistical weight factor for each transition energy level, the unit level is unity where GTR is 1. So for each transition energy, for different transition energy, you will be taking the unit as 1. And further resolving this, the equation 105, substituting the ETR in equation 105, it will be 1. And further, transfer energy levels are closely spaced. And this you go through this mathematical form in order to we'll be discussing about the problem here. Calculate the transitional partition function for 1 mole of oxygen at 1 atomic pressure where 25 degree Celsius, assuming the gas to be ideal. So they are given the temperature, the atomic pressure they are given, and the concentration where 1 mole of oxygen is taken. So we need to calculate the transitional partition function for a molecule. So partition function here is it is nothing but the ratio of total number of particles to the number of particles in the ground state. So transitional partition function, how you are going to calculate this is nothing but the equation from the previous. Yes, this is from the equation. A transitional partition function of a molecule. So QTR is equal to 2 pi mkt to the power of 3 to 3 by 2 divided by h cube into RT divided by P. So there we are going to substitute P is the one atomic pressure and temperature is, we should convert this in the degree Celsius. So plus 270 you will make it to convert it into Kelvin. That is the standard form where we are derived all in the Kelvin. And R is the atomic pressure where 82.06. K is the constant 1.38 into 10 to the power of 23 where h cube it can be 6.023 into 10 to the power of 23. The rotational energy of a molecule. And if the molecules are in the rotation, we are going to calculate the partition for their function. And that is the rotation energy of a molecule ER depends on the rotation quantum number. So it mainly depends on the quantum number of that molecule. That is denoted by J. And further, it also the statistical weight of this. Each rotation energy level is given by GR is equal to 2J plus 1, where ER is nothing but rotational energy. So this Q summation of GR into e to the power of minus CR by KT. It is the rotational energy of a molecule for ER dependent. ER is the total energy of the molecules present in that system. So for the deriving, you'll get the equation 16, 116, zipping for diatomic molecules to be a region of rotator where can be written as ER is equal to h square by 8 pi square I into j plus 1, and I is the moment of inertia, mu is the reducing mass, and r small r is the internal nuclear distance, the distance between the two nucleus, internal nuclear distance, and M1 and M2 are the masses of that atoms in diatomic molecules. So there will be two different molecules that is known for diatomic. So the masses of that atom are M1 and M2. This is the equation 121, that is for the rotation partition function. It can be sigma, where sigma can be written as the symmetry factor. Here you need to calculate the rotation partition function. So rotational partition function, that is denoted by QR, where this is what the derived from this the formula, where it has been derived from this equation 121, and further taking sigma n square is equal to 2, where n2 is having 2 molecule and 13.9 into 10 to the power of minus 4, where k is the 1.38, and temperature 273 plus 25, and height of that system where 6.624 into 10 to the power of minus 27. So these things all will be given in the problem itself. So you just need to insert this formula and calculate the value of that. Vibrational addition function, that is denoted by QV, where the energy of a linear harmonic oscillator is given by expression. To determine the vibrational partition function, EV is equal to V into V plus half 1 by 2 into H theta. So here V is the vibrational quantum number. So vibrational quantum number, and this is nothing but var theta. Vibration energy of a molecule in excess of 0 point energy is given by, and further the vibration partition function is given. EV is equal to VH of theta, that is the equation 125, and QV is equal to summation of GV by e to the power of minus by QT, where here C also, it is the velocity. So next is the electronic partition function. Here the statistical weight factors for the electronic energy level, where J is the electronic quantum number, and electronic energy level, it can be G is equal to 2J plus 1, where J is the electronic quantum number. Q is equal to summation of G into e to the power of e minus kT. This for the temperature. The atoms of molecule remains in the ground state. Electronic energy separation is very large. Here the electronic partition function for the moderate temperature. The atoms and molecules remain in the ground state. Electronic energy separation are very large. So electrons or molecules will be in the ground state itself. And next is the total partition function. Again, the ratio of total number of particles to the number of particles in the ground state. So means the partition function here is nothing but the ratio of total number of particles to the number of particle in present in the ground state. So that is known for partition function. How to calculate for total partition function? It is nothing but Q is equal to Q translational partition function, rotation into rotational partition function, and velocity of partition function, and energy of the electronic translational partition function. So further, all QTR, QR, and QB and QV is derived in previous So from that, what you are going to insert those equation here. Q is equal to, you are going to take the for transfer energy, that is 2 pi kT divided by h cube to the power of 2 3 by 2 into V. That is for Q transfer and remaining Q rotational and Q velocity and Q electronic transition. That is the equation to calculate 134. That is the equation for total partition function. So in the summary of this unit, the partition function comes from a way of counting particles in a system. So the particles are distributed over the available energy levels. Partition function is nothing but the way of counting the particles in a system. So that is the summary of this unit. And next, we are going to discuss about the basic functions of thermodynamics in the internal energy, entropy, and moles free energy, pressure, Gibbs free energy, enthalpy of that, and further the equilibrium constant for partition function and heat capacity for behavior of the solids in classical thermodynamics. Partition function is a essential uh, for the linking of the coordinates of the microscopic system to thermodynamic properties. So it is very, the partition function is very essentially linked, and all the physical properties such as entropy, pressure, temperature, energy, internal energy, enthalpy. So this can be estimated. In the introduction, the concepts of statistical thermodynamics to calculate the chemically significant quantities. Uh, Here we are going to study about the concepts of statistical thermodynamics to calculate the chemical significant quantities. So studying about this to calculate equilibrium constant of a reaction. So for different reaction, the equilibrium constant of that be different. And through this calculation, we understand some of the molecules and their features, and also you can determine the magnitude of that equilibrium constant. And with the varying in the system, we can be varying with the temperature also. Bridge between the thermodynamics, spectroscopy, and quantum mechanics. So the partition can be used to calculate thermodynamic function, heat capacity, entropies, and equilibrium constant of the system. So evaluating the thermodynamic function in terms of partition function. Utilizing the partition function and Maxwell-Boltzmann distribution law for the equating the various thermodynamic parameters for internal energy. First, is the internal energy. The internal energy of the system containing n molecule is given by E is equal to summation of Ni plus Ei. Ni and Ei are nothing but the energy of the molecule present in that level. So according to Boltzmann, Maxwell-Boltzmann distribution law, Ni is equal to the equation followed, and further E is equal to summation of E is nothing but the internal energy in a system. So E is equal to summation of Ei into n by q e to the power of e minus I divided by kt. The equation n by q summation of, when it comes n by q summation of e I into e to the power of e minus I minus ei divided by kt. That is the equation 135. But q is equal to summation of e, that you are going to substitute in that equation 135 with respect to t, differentiating with respect to temperature, keeping t as a constant. and further that is the equation 136 we are going to give, and substituting the equation 136 in the 135. So the value of summation of e to the power summation of ei into e to the power of minus ei by kt. You are going to substitute this value in the equation 135. That is the equation 137 you are going to get. That is for internal energy. While you are going to calculate the entropy. Here, what is entropy? Means entropy. The higher the entropy, the higher the disorder of the molecules. So, measure of number of ways of the system can be arranged by entropy. So, S is denoted by entropy. S is equal to K to n ln of Q plus K into beta E, where beta is equal to 1 by K T. Therefore, S is equal to beta. You are going to substitute in that equation. Further, we'll get the substituting E from the equation 137. So, this E you are going to substitute in the entropy. So, we'll be getting the equation 138. And further, Hammond's free energy. We are going to calculate where Hammond's free energy A. Here A is Hammond's free energy A is equal to E minus Ts. So yes, we are going to substitute what we have got the entropy from the system. E is equal to minus T into S value. That is the equation 138. You are going to substitute in this to get the Hammond's free energy. And further, for pressure, A is equal to Ts. Yes, you will be knowing. And dA is equal to d minus T, ds minus S dt, dq. Further, at constant temperature, dA by dV into to the power temperature in minus equal to minus pressure. Where taking negative on right hand side to the left hand side can be written in the equation 140 is equal to RT divided by Q into dq by dV of temperature, where RT is equal to d ln of Q divided by dt. And further, how to calculate about the Gibbs free energy? G is equal to A plus PV. We will be getting the value of P also. Will be A is also available from the previous equation, that is for Helmholtz uh, free energy. This is the equation of Helmholtz free energy. That is the equation number 139. So from that we are going to calculate the G also. That is equation 142. And for the enthalpy are also heat content of the system. H is equal to E plus PV, where H is the enthalpy. So E P we have calculated, and we need insert the value of pressure is equal to that one. We are going to take it in the equation for calculating the heat constant, H is equal to E plus PV. So further calculating for CV, CV is equal to d by dt of volume. So with respect to volume, where CV is nothing but the heat capacity, and E is equal to RT square by d ln of Q by dt. So dCV you are going to substitute in the equation, and you will get the value of 144. And further evaluating the equilibrium constant from partition function, we know that E is equal to E naught plus RT square d ln of dt. That is the equation 145. And further substituting the value of E naught, and also we know the value of R, consolidated energy and entropy with Almond's free energy, that is the A, and pressure P, and Gibbs free energy G, and enthalpy H from the previous. So here we are evaluating of the equilibrium constant for partition function. So we know that E is equal to E naught plus RT square into d ln of Q divided by dt. That is the equation 145. Substituting the values of E and S, will be we are knowing the value of E and S. So it can be written as G is equal to E plus R minus PS. So here you know the value of E and S. Yes, E is the internal energy and S is the entropy. So that values you are going to insert in the equation 147. You are inserting in the value in the equation 147, that is E and S energy and system. So G is equal to E naught minus RT ln of Q by N, that is the equation 148 after substitution of this, where we know that H is equal to E plus PV, where it can be written E is equal to RT for H. H is the enthalpy. So enthalpy of energy, H naught is equal to E naught, means the molecules present in the E naught energy level 0. So the enthalpy heat content is equal to the energy of the system, energy in the level 0. So it can be written as G naught is equal to H naught minus RT ln of Q by N. That is the equation 149. So further considering the homogeneous gas reaction, ABC are the small ABC are the number of moles for the reaction A plus B gives rise to C plus D. So yeah, delta G naught is equal to delta G naught D and C G naught concentration A and B. And G naught is the Gibbs free energy of the energy level 0. After substituting those equations, you are going to get the value of delta G naught, where that is the equation 150, and here delta G naught is equal to minus RT ln of Kp, where Q positive is the energy transferred into the system, where Q is in the positive mode means it is the energy transferred into the system. Is in negative means energy transferred out of the system. So that we are going to calculate here. Q is equal to QTR into QE. Q be the independent of the temperature. The molar entropy is given by S is equal to this the equation 79, where we derived the equation 79. Previous CDK unit ಹೋಗ್ಬೇಕಾಗುತ್ತೆ transition energy. So it is the equation 79, and that S value you are going to insert in the equation 152. We'll get the After substitution, we'll be getting the equation 153 here. So next you're going to M, where molecular weight of the substance you're going to substance and pressure at 1 atom pressure, the molar entropy of the substitution behaving. S is the molar entropy of the system. So if you calculate inside that value, that we'll be getting the equation 154. And the problem, calculate the standard entropy of atomic chlorine. 25 degrees Celsius, where Q is 4.03. Uh, this equation is from here. We are going to substitute the values where M is equal to mass temperature and energy is 4.03. So entropy of that system will be 39.4 calorie per degree per mole. And comparison of third law with statistical entropies. This we are going to compare with the third law of thermodynamics. And here entropies of substance calculated using third law of thermodynamics, and it is called as law of entropy. So, or thermal entropy. While it is calculated with the Boltzmann-Planck equation, that is known for statistical entropies. So here it is found that thermal entropy are lower than statistical entropies. What is the difference between the thermal entropy and statistical entropy? Means the entropy is derived from the third law of thermodynamics, and the entropy which is derived from the Boltzmann-Planck equation, that is known for statistical entropies. We are deriving deviation of ranging from 3.1 to 4.0 joules per moles. One can conclude that entropy substance such as hydrogen, deuterium, carbon monoxide, nitric oxide, and the nitrous oxide, water are not at 0 Kelvin. So the third law is finite. So the entropies are called residual entropies. The third law predicts it is infinite with the system. The existence of the residual entropies at crystal 0 Kelvin is probably due to alternative arrangement of the molecules in the system. So here some of the alternative molecular arrangements means in a system it will be different arrangements of molecules will be taking place. It is for carbon monoxide and nitrous oxide, where nitrous oxide is also known as laughing gas. So here there are two different systems. One is which is having different arrangement of molecules at 0 Kelvin. Here 0 Kelvin it is will be around 300 degrees Celsius. The molecular arrangement taking place. So when 0 Kelvin, each molecules can assume two states. There are entropy of a crystal containing n molecule is given by mm, The molecule assumes to be in the two state. The entropy of the crystal containing N molecule is given by S is equal to K ln of W, where N is the Avogadro number, S is the entropy of the system. So the occurrence of residual entropy in ice is also attributed to the molecule's disorder at 0 Kelvin. From this, what you are going to analyze here means the disorderness of the molecules can be seen at 0 degree Kelvin. No, sorry, 0 Kelvin. So disorderness of molecules, molecule rearrangement, alternative molecule arrangement at 0 Kelvin. And next is the heat capacity behavior of the solid. So this is the classical thermodynamic approach. The constitute particles take up equilibrium position for minimum potential energy. The force of attraction or repulsion exact between each other. So here, uh, Dunlop and Petit found that the product of atomic weight and specific heat of solid element was constant, but solid elements have the same heat capacity per gram atom. Means the heat capacity of that atom will be same for all the atoms, but it failed here. The atoms of all the elements have the same heat capacity was described by Dunlop and Petit. This statement may be taken as the statement of law of Dunlop and Petit. So these are the atomic weight of different elements where their heat capacity was in the approximate of 6 to 6.2 to 6.4. So here the vibration also occurs in three dimension where PV is equal to 1 by 3 into N to M C bar square. So Nm is the number of molecules, M is the mass, and C square is the mean square of the C by square is the mean square of the velocity. So vibration may occur in three direction also. In each direction, 2 degrees of freedom, and each degree of freedom will have energy of 1 by 2 kT. So vibration may occur in all the three directions of the molecule, X, Y, and Z. So each direction it will be having 2 degree of freedom, and each degree of freedom is will be having the energy of half kT. So further, PV is equal to 1 by 3 Nm C square, that is RT, where CB is equal to 3R3 into 1.9872. The heat capacity of almost it was ranged in between 6.2 to 6.4 degree for all the range of atomic weight. From atomic weight of the molecule 7 to 38. All were in the range of the heat capacity were in the range of 6.2 to 6.4. For some of the certain elements, it showed especially low heat capacity. The values, the heat capacity were generally it were from 6.2 to 6.4. For some of the elements, it showed around 3.5, 2.5, 1.5. Uh, for diamonds, it was around 1.35 and 4.7. And for silicon, it was around 4.7. So this law of Dunlop Pettit failed for some of the elements. So that is what we are given. The heat capacity are almost 6.2 range, and the atomic weight for 7 to 238. and certain elements were showed very less 3.2, 2.5, 1.35, and for diamond the temperature at -50, the heat capacity was around 0.76. At the temperature of 10 degree it was around 1.18, and at the temperature of 35 it was around 2.1. Was applied to all the substance at elevated temperature. Means the incorrect, this was incorrect. However, for heat capacity of those elements which appear to obey the law of ordinary temperature. So the observation of this atomic capacity for 6 calorie degree has shown to be theoretically significant for the atomic weight of the molecule from 7 to 238. And quantum theory of heat capacity. So here, two new theories were derived from the heat capacity, that is Einstein theory and Debye theory. For this, a specific heat increases with temperature, and effect is more marked from the light elements whose heat capacity is exceptionally low. That is the quantum theory of heat capacity. Here, two theories were derived. That is, one is Einstein theory and one more is Debye's theory. So, first in the Einstein theory, when the applied quantum theory to the problem of heat capacity of solids were shown here, and the E bar is the energy of vibration. So E bar is equal to h theta divided by e to the power of s theta by kt minus 1. That is the equation 155. For 1 gram of atom of elements can over be regarded as the system of three number of linear oscillators. Mean 3, n being Avogadro number. The average per gram atom is given by E is equal to 3n into, that is the equation 156, and the Einstein equation of the heat capacity at volume, constant volume. So here heat capacity at constant volume, that is Cv. So Cv should be approached 0 or very low to temperature, where at high temperature h theta by kt is small comparison of that unit. In general, these elements which constitute exceptional for Dunlop and Petrite law having high value of theta, where the characteristics is. So from this theory, what are the limitations? It can be Einstein theory fails in predicting the heat capacity in lower and intermediate temperature. So the values predicted by its lower than those have actually observed. Here from this, the temperature what we have got for the heat capacity value fails to explain for lower and intermediate temperature. So if the heat capacity of that is less, means it cannot be found out by Einstein's equation, that is the equation 157. So one more theory was derived here by Debye equation. So in this, Debye developed a modified equation which gas a very satisfactory agreement with the experimental over entire range of temperature. So it can be applied for entire range of temperature. A solid is assumed here. A solid is assumed to be elastic body. So its solid should be in the elastic body in the system, and vibration of those whole should be considered. Whole system molecules should be considered for the vibration. And the three n modes of the vibration are not all identical. Means when the molecules are vibrated in the three directional x, y, and z, all direction it won't be in the identical and are disturbed among the spectrum of frequency. The frequency range from theta is equal to 0 to maximum theta m. So theta and theta plus dV is the frequency range of that particle. V is the vibrational frequency and Z is the elastic medium. So it can be written as dz is equal to 4 pi V divided by C cube into theta square dy, where by integrating with respect to n atoms, we'll get the value of V. That is the equation 160. V is the vibrational frequency. So substituting the V in the equation 158 again here this value. The total energy of the gram atoms for solid, that is the equation 162, and further equating the equation 162 can be written as wherein the value of x is equal to h theta by kt and theta is equal to kt by x, that you are going to integrate in the insert in the value of one equation 163, where the equation 162 can be written as consider the heat separately for high and low temperature. So we are going to calculate the heat capacity separately for high and low temperature. When the temperature is high, x is small. When the temperature is low, x is large. This is what they are given here. And CV, you are going to calculate the heat capacity, where should be knowing the equation, that is the 168 CV, where 464.4 into T by theta, that is the power of cube, where you can know the D by thermodynamics third law, it is applicable for low temperature below 20 Kelvin. So this D by equation can be applied for the temperature below minus 20 Kelvin, means minus 273 divided by minus 20, it will be around minus 253 degree Celsius. It can be applied till 250 degree Celsius for very low temperature also. From this, you are going to see this CV is the heat capacity. This is for the Debye theory, and this for Einstein theory. These two are for the quantum theory of heat capacity. So the Debye equation predict here that heat capacity of a solid is function of temperature and depend upon only the characteristic maximum frequency. So that is nothing but the theta m. So next is the Debye characteristic temperature for some of the examples they are given here: sodium, copper, silver, trash, where theta value having the temperature of 159 degree, 100 degree, 3 and 13 degree. Some of the examples they are given for solid, silver, carbon, iron, nickel, aluminum. They were given here for different temperatures. And further Debye characterization for temperature theta. So it depends on the nature of the metals in the characteristics temperature, which is related to the characteristic maximum frequency. So the only quantity in the Debye treatment that is dependent on the nature of the metals in the characteristic temperature. So the nature of the metal also it depends for the temperature of that compound molecule. So it is related to the characteristic maximum frequency, and the energy may be stored in the molecules in that are liberated. So theta is equal to h theta m divided by k. The value of theta can be determined for the measurement of heat capacity value. So summary of this equation of this unit. So a partition function is essential link between the coordinates of microscopic system and the thermodynamics property. And here the physical properties such as U.S.C.P.V. pressure, volume, etc. can be estimated. And energy may be stored in a molecule in various modes. The total energy of a molecule is calculated by E is equal to E trans, that is what, and degradation of energy also multiple will be taken, where